Today we're going to be talking about two types of functions, exponential and logarithm functions. So, an exponential function is when there's an x as your exponent, and f of x equals a to the x is an exponential function with the base being a. The domain of this is all real numbers because I can plug in any x I want, but my y outputs are never going to be negative. So that's going to get me my range of y is greater than 0. Making the x asymptote, or y equals 0, your asymptote. And we have a growth function or a decay function, and that all depends on a few things. First, I want to talk about a few key points that we're going to first be graphing. Okay, so one of the key points is if you make your exponent negative, you get 1 over a. Make your exponent 0, anything to the 0 power is 1. And then 1 and a. And that's going to get you an idea of what the graph looks like when we start translating. Now, a growth function is as x gets really, really big, your y's also get really, really big. And a decay function is as your x's get really big, your y's get infinitely smaller. And both approaching that x-axis, which is your asymptote. Okay, graph that function, state the domain, range, and asymptote. And I'm going to write myself a little note here. Domain, range, and asymptote, so I remember to do that. Now let's talk about our translations. -3 means I move everything down 3. So this x-axis that was my asymptote, I move down 3 units. And I draw that in right away so that I know that that's like a floor I can never cross. And then +4 means I move everything left 4 units. So what I need to remember when I'm graphing is that I'm graphing translations of the 2 to the x function. So if I'm graphing translations of that, I find those key points that I talked about, and I translate these points is what I typically do. Anything to the 0 power is 1, get with it, and then 2. Okay, so what I do is I plot the point -1, +1/2. I translate this down 3 units, 1, 2, 3, and over 4. And I do the same thing. I have 1, 0, down 3, over 4. And then we have 1, 2, so, 1, 2, down 3, over 4. Remember, it's not a line, it has some curve to it. So our domain is all real numbers. The range, y is greater than whatever your asymptote was, which was -3, and your asymptote is -3. And this should be a review from both Algebra 2 and Pre-Calculus. That's why I went through that fairly quickly. Okay, one-to-one functions. This is important. When a function has one input, so each output is associated with exactly one input. So you have a couple different ways that we test. Well, one way that we test that is the horizontal line test. This function y equals x cubed is 1-to-1 because it passes the horizontal line test. Your graph only intersects at one point. Versus y equals x squared, that does not pass our horizontal line test. And what this means is going to be on our next slide. So inverses. So since each output of a 1-to-1 function comes from just one input of a 1-to-1 function, you can reverse them and find an inverse function. So if a function's 1-to-1, the inverse is a function. I can find the inverse of anything, but then the ability to be able to solve for y and to write it as an inverse, this is the notation we use for inverses, tells me that it is a 1-to-1 function. Now, composing a function with its inverse and you get back the value of x, that tells me that we have an inverse. In this example, we need to find the inverse of this function. Remember how we find the inverse is we switch the x and the y. F of x is a fancy name of saying y. So I have x equals 2y plus 3 over y minus 4. Now cross multiply the y minus 4 over to the other side is equal to 2y plus 3. Now I need to solve for y, so let's isolate any term that has a y in it. So I have xy is equal to, not equal to, Marnell, minus 4x equals 2y plus 3. So let's get any term with a y on it to one side, any term that doesn't have a y on it to the opposite side. So I'm going to basically switch the location of this 4x and this 2y. Factor out your y. And then y equals 4x plus 3 over x minus 2. So therefore then our inverse of this function is 4x plus 3 over x minus 2. Now finding the inverse for this function. So I switch my x and my y. Now remember how we solve for exponents, our logarithm. Log base 2 of x is equal to y plus 7. Subtract the 7 over. And we have now our inverse. So a new function is born. Hey, these two functions are inverses. That's why the domain of a log function is the range of its inverse. And the range of a log function is the domain of the inverse. And then remember that we have a few special functions. Log base 10 is called the common logarithm. And log base e is the natural logarithm. We use this log base e a lot in calculus. Okay, so base A and base E, these two things are the same thing. And what students don't realize, or what I think pre-calculus teachers might do a bad job of explaining, is why are these properties true? Well, if I make f of x the function a to the x, and I make g of x the function log base a of x, when I take my composition of f of g of x, which is this quantity right here, you simplify and you get x because those two functions are inverses. Now graphing logarithms. Okay, graphing logarithms. This is very, very challenging for many students. So normally we have this log base 3 of x plus 3. That moves our asymptote, which is normally the y-axis, 3 to the left. This 4 moves all my points up 4. And then the 2 is a y multiplier. So normally what we have is we have translations of this graph. Y equals log base 3 of x. So let's come up with some common x and y points. Mr. Hirsch does powers of the base. What I sometimes like to do is I like to convert this to an exponential because that's just easier for students to understand. Now pick nice numbers for y. -1, 0, 1. When I plug in those, I get 1/3, 1, and 3. Okay, now to get to graphing this. Normally, we have the vertical asymptote being the y-axis. That shifts over 3 units, 1, 2, 3. I think of that as a wall. A wall we cannot cross. Unfortunately, with our political climate right now, that's really hard to say, but I think of that as a wall. That's a wall between myself and Mr. Hirsch's room. You don't want to go into Mr. Hirsch's room. You want to stay in my room. Okay, these are the points we're going to shift. So normally I have -1 and 1/3, but I need to shift that over 3 units. So 1, 2, 3, and up 4. 1, 2, 3, 4. Ooh, but I have this y multiplier. I apologize. Let's do this first. We have our x's. We have our y translation. Now what I'm going to do is I like to lay out this chart. It just makes it easier. We have 2 times this function plus 4. These are these normal points that we just came up with. X was 1/3, 1, and 3. Okay, the x's get subtracted by 3, so this becomes a 0. This becomes a -2. This becomes a -2 and 2/3. What I'm just doing is I'm plugging these x values in here for x to get my new x coordinates. Now plug these y coordinates in here for y. 2y plus 4. That's how I got that 2y plus 4. So -2 plus 4 is a +2. We have a 4, and then we have a 6. So now what you're going to graph is you're going to graph this column versus this column. So -2 and 2/3, that was my 2, and a +2. We have a -2 and a 4, a 0 and a 6. And I just want you to know in general what a log graph looks like. So it generally looks like this. This is just getting you some points, but you need to know this general idea. Now the domain and range, this is what I always forget on these problems. That's why I have to redo this for this year. Domain. Your domain, it's our wall we can't cross. X is greater than -3. Range is technically all real numbers because our graph goes infinitely down and infinitely up. Our asymptote, x equals -3. Just a quick review of our properties of logarithms. You're going to need these when we start talking about some stuff later on in calculus. Okay, solving this guy for x. We add 9 over. Now you use logarithms to solve. Log base 2 of 17 is equal to x plus 5, and then I subtract 5 over. Using the change of base formula, this approximates to -0.913. Lastly, solving this for x, I need to break this 4x out. So e to the 3y plus 8 is equal to 4x. So I write it now as an exponential because remember logs and exponentials undo each other. Divide everything by 4. That's what we get when we're solving for x. Again, there is a Google form right below the video. Please make sure that is submitted on time.